All right, welcome back, everyone. So how'd the homework go for 6-2, that first part? Fun?
That's not too bad, but yeah. How far were we supposed to go on it?
Well, I mean, the first 36 problems, you know, any of those would have been good practice.
Okay.
We have not done the second part of the assignment, which we're going to talk about more today. But if you did go through those problems, you can attest to the fact that there's a lot of things in there that we didn't necessarily go through in detail in class. The basic idea is there, but some of those problems required a little bit of work before you even get to the type of integral that we looked at in class. So again, kind of stressing the fact that the homework is an essential part of this class, that it's impossible to expose you to every single scenario in class. So we try and get the basic idea down, but the homework is where it's really going to happen. So, okay, well, I did send an email a little while ago about the quiz, and the quiz is going to be due today at 5 o'clock, and I gave a Dropbox for you to put that there. I think after today's lecture, if you were having any problems with that quiz, you'll have enough after today's lecture to finish the problem up. Okay. All right. So,
but we just have until today at 5, right? Not tomorrow.
Yeah, today at 5. I want to see, because you should have had something ready right now. So if that's still all you have, just send that to me. It's better than nothing, but I'm going to give you a little extra time to finish the problem out if you weren't able to finish it.
Yeah, I wasn't able to do that.
Okay.
So because after the class, I got stuck to the part where we were about to substitute. So I just wanted to know that if we submit it right now, so are we going to get any type of extension or something?
Well, what I would expect that what I'm going to look for is, were you able to turn it into a trig integral using a trig substitution? And then once you got it to the trig integral, were you able to evaluate that trig integral and get an answer in terms of theta? Now, if you got that far, I'm happy. All right. The rest of it I hadn't shown you, and we'll cover that today. But at least that part is what I was hoping you'd get to. Now, if you didn't get it over to a trig integral, then there's an issue there, because that means you weren't able to follow the trig substitution, which is what we talked about last class. So turn in what you have. Let's see what the class turns in, and then we can talk more about extension or something like that. Okay, let's get into this. My goal is to try and get through 4 problems today. That's it, 4, that's it. So let's see how it goes. All right, so here we go. We're gonna go through this first one. We have the integral 1 over x squared square root of x squared plus 9 dx. All right, let's just work with this. All right, so we go and, again, we go through this idea of, okay, can we do this without any crazy technique? Is there a basic U sub here, integration by parts, and pretty much nothing's going to work. Like you can't let U be x squared plus 9, because the derivative of that, du, would be 2x dx. We don't have 2x dx. We don't have x dx. We don't care about the 2, but we don't have x dx sitting there by itself free somewhere. We have an x squared, and yes, you could take this equation and solve it for x squared, right? So you could rewrite the x squared. You could rewrite the x squared plus 9 in terms of u, but you don't have any way to easily turn the dx into something in terms of u. So we're stuck, right? But we see the square root, right? We see the square root. And because we see the square root, it falls into one of those forms, right? This square root down here looks like we have the square root of x squared plus a squared, right? That's what it looks like we have. And if we go back to the formulas from last time, right here, the square root of x squared plus a squared is the same as this one. It's just changed the order, and addition doesn't matter, right? It doesn't matter if you have a squared plus x squared or x squared plus a squared. So I know that I can make a substitution that x is going to turn into a tangent theta. And then remember last time I told you could add to this, right? What did I say you could add? For this, we said you could put on here that that thing will turn into a cosine theta, that this thing will turn into, anyone write it down?
A secant theta.
Secant theta.
Theta. And that this one will turn into
A tangent theta.
a tangent theta. So I'm going to use this form. That's the form I have in the integral. I'm going to make this substitution, and that big ugly thing is going to turn into a secant theta. All right, that's what I'm about to do. Okay, so I'm going to make my substitution now, my trigonometric substitution. X will be equal to, what's a for us?
The whole thing, right?
3, right? The square root of 9, which is 3. And then we're going to be doing, I already forgot.
Tangent theta.
Tangent theta, right? Now, we know that the square root of x squared plus 9, without actually showing it, we know that that's going to turn into 3 secant theta, right? We worked through that in class last time, but I'm just going to write it down now. We also need to take this and take its derivative so that we have an expression for dx. So if we take derivative of 3 tangent theta, we get 3 secant squared theta d theta. All right, is that clear to everyone, what I've done? Any questions?
Yep.
Okay, we're going to rewrite the integral now in terms of theta. So we have integral 1 over, okay, let's talk about x squared. X squared should be this x squared, right? So I need to square 3 tangent theta. So that should give me 9 tangent squared theta. So I'm squaring the 3 and I'm squaring the tangent. And then I have to take care of the square root of all this crap right here, but I already know the square root of all that crap is going to be this, 3 secant theta. And then I have to rewrite what the dx is, but I know that the dx is going to be 3 secant squared theta d theta. So times 3 secant squared theta d theta. So I have transformed the integral now. It is now a trigonometric integral. And so I'm going to do some simplification now. Let's see, I've got this 3 and this 3 cancel. One of the secants goes away, right? And I still have that 9 on the bottom. So I'm going to pull the 9 out as a 1/9 integral. I still have a secant theta on top, and I have a tangent squared theta on the bottom. All right, now, remember we have those formulas that tell you how to deal with secant and tangent? We cannot use that because the secant and the tangent we have here are separated. One is in the numerator, one's in the denominator. So what did I say you should do if you ever get to a point where the formulas don't work or it's not in the right format, but you've got trig stuff?
Change the for sine and cosine.
Yeah. Rewrite everything in terms of sine and cosine. So I'm going to rewrite secant as 1 over cosine. And I'm going to rewrite tangent squared as sine squared over cosine squared. And then I'm just going to flip it, right? So I'm gonna get rid of this down here and flip it and multiply. So cosine squared theta on top sine squared theta on the bottom. And when I do that, one of the cosines cancels. And so we get a new integral, 1/9 integral. See, I have one cosine on top, and I have sine squared on the bottom. Is that good? Any questions?
Could you explain real quick where that 3 secant theta came from?
Where the
X squared plus 9, the square root of x squared plus 9 equals 3 secant theta.
okay, so we showed that in class. I'll show it again. The thing is, we don't want to have to do that every single time, but I will show one more time how this works. If we make this substitution, replace x with 3 tangent theta, then let's just write down what square root of x squared plus 9 would be. It would be the square root of, well, x squared, right? Well, what's x squared? It's this thing squared, right? So put in here 9 tangent squared theta, and then you still have plus 9. You factor 9 out. And then you use the Pythagorean identity to rewrite that, right? Tangent squared theta plus 1 is going to be secant squared theta. That's the definition, or that's the Pythagorean identity. And now you can take the square root of each one, you get 3 secant theta, which is why that thing turns into that.
Awesome. Thank you.
Okay. So if you want to go through that each time, you can, or you can just write it down on your formula sheet. You know, it's up to you. There's nothing wrong in going through this little algebraic exercise, right? There's nothing, I mean, it's not going to hurt you, other than time, right? On a test, that would be time you're eating up. Okay, so here, we're okay? Any questions on any of this here, or canceling? Or
So the
anything?
only thing we did on the canceling, basically we just cancel the one cosine, right? With the cosine square.
Yep. And then we left the sine squared on the bottom.
Okay. Yeah, because I saw the big cross and everything, but I said, oh, maybe.
Yeah, no,
It just
what I did is I rewrote, instead of dividing by that, I multiplied by its reciprocal.
Oh, I see.
Right, that's what I did.
Mm-hmm.
Okay,
So
now what?
I have a question.
Yes.
Over on the, before we turn it into sine and cosine, couldn't you have just done u sub with that right there?
Okay, what would your u be?
Wouldn't it be tangent squared theta?
Okay, so if I did a basic u sub, if I did u is equal to tangent squared theta, then du would be, the derivative of that would be 2 tan theta times secant squared theta d theta, chain rule, right?
Right. Okay. I see. I see where I messed up. Okay.
So that right there, obviously we don't have that. So we don't have
Right.
du.
Right.
So we can't go that route.
Okay. Thank you.
Good question. So on this integral, what are we going to do? I mean, we're here now, we've got sine and cosine, big deal. Like, does it help us or not? You can't use that formula sheet, right? You can't use that little cheat sheet for sine and cosine because, again, the sine and cosines are separated. They're not both up in the numerator. You have one in the denominator, one in the numerator.
Do you make them into 2 different
Can we flip
fractions?
everything to secant in terms of secant and tangent?
You could go back. You could go back. Brian, what did you say?
Could you separate them into 2 different fractions?
You could do like multiplication. You could make it like cosine theta is 1, and then the other one is 1 over sine squared.
Yeah, and then I think 1 over sine theta is,
Cosecant.
yeah. Could you do that?
You could. That algebraically is correct. But I think all of you are trying too hard on this.
We just do a u sub.
Okay, what's the u sub?
Sine is
Sine squared theta or
Sine.
sine theta.
Just sine theta, because you have to go back. it's almost like every time you get to a new integral, you just want to like hit the reset button, right? And you just want to go, okay, can I handle that now? So you start thinking, okay, let me think u sub. Do I see something in its derivative? Well, I see sine theta, right? It's squared, but I see, if I look at just the sine theta, I have sine and its derivative is cosine. I have that derivative up here, right? So we can just do a basic u sub. U is sine theta. Du is cosine theta d theta, which we have. And so now I can just rewrite this as 1/9 integral. Okay, so the cosine theta d theta is really just du. So I'm going to put du on the outside. That takes care of the blue part, right? And I still have the yellow part squared. So I'm going to put 1 over u squared. That's 1 over sine squared, basically. And be careful that the antiderivative of that is not natural log, right? Because it's squared. So you
We
have
need to bring it up.
Yeah, bring it up. And now use your power rule. So the antiderivative of u to the -2 should be, you're going to get a negative that pops out.
1
So
over u.
-1. Go ahead.
That's 1 over u plus c, right?
Yeah, it'll be 1 over u plus c. Just don't forget that negative comes out, right? Because you have n is -2.
Mm-hmm.
So you add 1 to that, you get -1. So technically you're getting this 1/9 times 1 over -2 plus 1 u to the -2 plus 1 plus c. That's your power rule. This right here just becomes a -1. And so that's why I just made the 1/9 negative. So this is going to be, I'll write it this way, -1 over 9 times u. Just going to put it all together in one big fraction, plus c.
Mm-hmm.
Now u was sine, so -1 over 9 times sine of theta plus c. At this point, we cannot be done because our answer is in terms of theta. We've got to get back to x. And so what was the way I did? I only gave you one example last class. So do you all remember how we get from theta back to x?
Right.
That will help out.
Triangle. We got to go to this substitution right there. X is 3 tan theta, and we have to come up with a triangle based on that. So on the side here, what I'm going to do is I'm going to write down x is equal to 3 tan theta. I'm going to isolate the tan theta by dividing both sides by 3. And then from that, I'm going to draw a right triangle. This is theta. Tangent is always your opposite over adjacent. So x should go here and 3 should go here. And I'm going to go back to the answer we had. Just tell me whether or not you believe that this is the same. So the -1 over 9 is like a -1/9 out front. And then we still have like a 1 over sine, and 1 over sine is cosecant.
Mm-hmm.
And cosecant is the reciprocal of sine, right? Sine is opposite over hypotenuse. So this should be hypotenuse over the opposite.
I have a question. Isn't that supposed to be the x? Shouldn't be on the other side when you're making the triangle?
Well, theta's here, right?
Yes.
Tangent, by definition, tangent is opposite over adjacent, right? So this
Sine
is
over
the
cosine?
opposite side, and this is the adjacent side.
Oh, okay, okay. I was thinking in terms of cosine. I thought it was adjacent over hypotenuse. I'm sorry.
Gotcha.
And
So to
wait,
get our, go ahead.
Isn't the hypotenuse always the square root that's in the equation?
It's going to turn out to be that way. Now, it's not always the hypotenuse, though.
Okay.
Sometimes it's one of the other sides.
So the remaining side that we don't
The
get
remaining
from our,
side, yeah.
Okay.
The remaining side will be the actual square root thing up here. It's actually going to be this.
Okay.
Okay, it will be. And we could confirm that just by doing the algebra here. This should be x squared plus 9, square root of x squared plus 9. So that side right there, you have to figure that out. just using a squared plus b squared is c squared. All right, so we need the hypotenuse over the opposite. So our answer is going to be -1/9 times the hypotenuse square root of x squared plus 9 over the opposite, which is x, and then plus c. There it is. That's the antiderivative.
Where did the cosecant came from?
I rewrote this as -1/9 times 1 over sine,
Oh,
and then 1 over sine is cosecant. I'm going to check the answer. All right, I'm going to check it, which means I'm about to take the derivative of that. Okay, so I'm going to take this, I'm going to take its derivative. So when I take derivative, the -1/9 is a constant, it comes along for the ride. Okay, so it's going to be out here. Now, the derivative of everything here in yellow is going to require quotient rule, right? Quotient rule from Cal 1. So I have to take derivative of the top times the bottom minus derivative of the bottom times the top. So I'm going to do derivative of the top first. The derivative of the square root of something is 1 over 2 times the square root of that something times the derivative of what's inside the square root times the bottom function. Then I subtract from that the derivative of the bottom, derivative of x is 1, times the top, all over the bottom, squared. And now I'm going to start cleaning this up. So my 2 here and 2 here cancel. I'm at -1/9 times, let's see here. These two x's go together, so x squared over the square root of x squared plus 9 minus the square root of x squared plus 9. All of this, all of it over x squared. I'm going to put these two together. Okay, and to put those two together, what I'm going to do is I'm going to realize that this square root is over a 1. So I'm going to combine them, getting a common denominator. So to do that, I have to multiply the top here by x squared, square root of x squared plus 9 over the square root of x squared plus 9. And now I can put them together. I realize this is a mess, okay? But I'm doing a check here, so. All right, so when I put those together, I'm going to have a new denominator, or not a new one. It'll be the square root of x squared plus 9. All of this is going to be over x squared. But my new numerator will be this x squared right there, minus, that's this minus sign. And then when these two multiply, the square root goes away. So I have x squared plus 9 when I put them together. But that minus is going to have to distribute. So I have that. Okay, what happens now? When I distribute the negative through here and through here, the x squareds cancel, and I get a -9 on top. So I have -1/9 times, I have a -9 on top. Underneath that, I have the square root of x squared plus 9, and over that, I have x squared. And this -1/9 can come back in and kill that off. Negative times negative is positive. And so I'm out of room. And so what I have is 1 over the square root of x squared plus 9, all of that over x squared, which I'll write as a fraction like that, x squared over 1. And then I will take this and flip it and multiply. So I put 1 over x squared like that. And that is the original problem. Right? It works, right? It worked. Was that a question?
So on this, again, for the test, we don't have to verify, right? That we get the right answer?
No. Mm-mm.
And
But I
if we
will
get
say-
at some point stuck, are we getting like partial credit for some of this stuff or no?
I mean, the partial credit will be determined on the path you chose, right? So if you did this problem and you tried to do this using integration by parts, you're not going to get much credit.
Yeah.
Now, if you use trig sub and you do the correct trigonometric substitution, that's going to get you partial credit. You know, if you get it down to this trig integral and get stuck, you'll get something, you know, so it's all going to depend on how far down the path you go. As far as checking the answer, you know how I came here and did the derivative? Like if you want to get good at differentiation, check your answers. Like if you want to become like a machine, you know, when it comes to taking derivatives, then checking your answers is really a great way, because all the algebra that I did here is just algebra, but you know, you have to be comfortable with it to be able to get it back to the original expression, right? Okay, let's move on to the next problem.
Hello, sir. I wanted to ask
Yeah.
a question.
Yeah.
For these kind of problems, do we use the integration by parts first, then use the trig substitution? Because that's what I'm doing for the quiz.
I don't think you need integration by parts first.
Uh,
As soon as you see the square root, you should be thinking trig sub. Just go straight to
okay.
trig sub. Now, I'm not saying that the quiz problem can't be done using integration by parts. It might. I have to go back and look at the problem, but I think it's probably going to be harder if you start with integration by parts.
But if we use it and we get the right answer, then we're good, right?
Then
Okay.
you're good. You might, it might be like 2 hours after you started the problem though. That's my concern, is that you may get the right answer, but it might just be that you just took up way too much time doing it. So,
Okay.
yeah, I mean, the right answer is the right answer, but there's efficient ways to do things and there's inefficient ways to do things.
Okay. Got it. Thank you.
Okay. All right. The next problem is 1 over the square root of x squared minus a squared. And here, just so everyone knows, a is a constant. We don't know what it is. All right. So a is not given to us. So we're just going to treat it like a number that we don't know. All right. So when we start this off and we're like, okay, I see a square root, right? I see a form that's on my formula sheets. I have something that I do when I see this form, right? When I see a square root, was it? Yeah, x squared minus a squared. I'm going to make a substitution. X is equal to a secant theta, and that square root thing is going to turn into a tangent theta. And then I'll have a trig integral, and I should be at least on the road to the answer. So my trig sub that I'm using here is my x is going to be, what was it again?
Secant theta.
A secant theta, right? So here a is just a, isn't it? Because they didn't tell us what a was.
Yeah.
So a is just a secant theta. All right. The square root of x squared minus a squared. I could go and show this. I could go work this all out, but I'm just going to go straight to what we know it should turn into, a tan theta. And then I also need what? What else am I going to need to do here?
dx.
Dx, right? So take the derivative of this. The derivative of a secant theta is a
secant theta, tan theta.
tan theta. And don't forget d theta.
D theta.
There you go. Now we rewrite everything. Okay, so 1 over the square root of all that stuff is a tan theta times dx, which is a secant theta tangent theta d theta. Right, so all we had to do was replace the dx with that, and we replaced the square root of all that junk there with a tan theta. That's the only thing that had to be replaced, right? We actually never even used this. Now, will we use it? Probably. We're probably going to use it when we draw a triangle. But for now, we didn't need it.
Because there was no x in front of the radical.
That's right. There was no x anywhere in the integrand. So I cancel the a's. I cancel a tangent. Hey, this is looking real good. Integral secant theta d theta. Now, your instinct right now might be to turn secant theta into 1 over cosine. But we did this problem in class last time. It was one of those 3 problems I did that are, this was the one where someone came up with this crazy number 1 that they put in there. I said, look, you don't need to know how to do this one. Just know that the answer is on your formula sheet. So we can go straight to the answer. Natural log, absolute value, secant theta, plus tangent theta, d theta. What number, what formula is that? Number what?
Was it 18?
I don't remember. I think it's
I
12.
think it's
14.
14.
So this right here, if you need to write down, this is formula number 14 on your formula sheets. That's what gets you from there to there. So we have an answer. It's in terms of theta. We need to get back to x, right? So let's just do a triangle. I'm going to take this information right here. I'm going to divide both sides by a. So I know that secant theta is x over a. Now I could kind of cheat right now. Isn't secant theta right there? Can't I just right now replace secant theta with x over a? Can I
Yeah.
do that? Okay, but I don't want us to be trying to avoid the triangle, because it's just the more problems you do, the better. Just generate the triangle real quick. Okay, now secant is the reciprocal of cosine, right? Cosine is adjacent over hypotenuse. So secant should be hypotenuse over adjacent. So I'm going to label the hypotenuse x, and I'm going to label the adjacent side a. And then if you use your a squared plus b squared equals c squared, you should be able to solve this side of the triangle to be the square root of x squared minus a squared. I think I'm going to show that step because I keep talking about it, but I remember as a Cal 2 student, that was maybe a little bit of a mystery. I'm going to call this side b. What we're doing here is we're using the fact that a squared plus b squared has to be equal to x squared. So I'm using the Pythagorean, right? And I'm solving for b. I'm trying to figure out what b is. So what I do is I subtract a squared on both sides. And then I take the square root on both sides. And I only look at the positive answer because we're talking about the length of a side of a triangle. That's where that comes from. So now that we have it,
And you said the secant was the opposite. What's 1 over
cosine,
1 over cosine? It's the opposite of 1 over cosine, right?
it's the reciprocal of
The
cosine.
reciprocal. Secant.
All right, so we can now replace everything. This is going to be natural log of the absolute value. Now secant theta, secant was hypotenuse over adjacent, so it's the x over a, plus tangent. Tangent of an angle is opposite over adjacent, so square root of x squared minus a squared, that's the opposite side on that triangle, over the adjacent side, which is a, plus c. There it is. You could combine these two together because they're both underneath the same, I mean, sorry, they both have the same denominator. You don't have to, but you could. And then this, that right there, on, if you did either one of these on the test, I would give you full credit, okay? But if you look in the back of the book or something for an answer like this, this is what they're going to have. So does anyone know why the book is going to do that? Why are they not even going to look at this A down here? Just ignore it.
Because it could be 1. I don't know.
It could be 1, and if it was 1, then yes, we could ignore it, but it doesn't always have to be 1.
Mhm.
So let me remind you of something about logs. Do you remember this property of logs? If you have division inside of a log, you can turn that into the log of the top minus the log of the bottom. So you can turn division inside one log, you can turn division into subtraction of 2 logs. This was a property of logs. Do you remember that property from college algebra?
Mhm.
Okay, so if I use that property on this, then what I have is the natural log of the absolute value of the top, right? Minus the natural log of the absolute value of the bottom. And then we still have plus C, right? But what's natural log of A? A is a number, right? A is some number. You don't know what it is. But the natural log of a number is going to be a number. Correct?
Yes.
So it's some number that I don't know, plus some number that I don't know. So you can group both of these together and just call that some number you don't know. Right? So they incorporate the natural log of A with the C and say, okay, it's some new number we don't know. Excuse me. So again, I would give you full credit if you stopped at, one of these, but if you look at the back of the book and you're like, what in the world? What happened? It's just a property of logs and putting those constants together. Okay. That was the second one. We're doing good. We're only 40 minutes in. 2 more to go. Oh my goodness, that one does not look good. Let me move that over here so I can see it over here. X cubed over 4x squared plus 9 to the 3/2. Okay, so this problem is it's gonna feel like we just jumped like from the frying pan to the fryer, or to the fire. Sorry, that's the saying, right? From the frying pan to the fryer, or to the fire. All right. All right, so the first thing that you have to recognize to be able to do this problem is you have to recognize that the denominator is actually the square root of 4x squared plus 9
Cubed.
all of that cubed. Exactly. That's what it means to raise something to the 3/2. It means you're taking the square root of it and cubing it. Now we have something that looks a little bit more like the form that we see with the trig sub, right? But there's a problem. The problem is the 4. In the formula that we have, here we'd be looking at the formula where it was square root of x squared plus a squared, right? That's kind of the form we have. Right, in that formula, there's a 1 in front of that x squared, and you can't just have it be whatever you want it to be. It has to be a 1 if we're going to use the formula. So what I'm going to do now is I'm going to get rid of the 4. So watch me get rid of the 4. It's going to be just algebra. When I say rid of it, I'm not completely getting rid of it. I'm just going to make my life a little better. So here's the cubed. So here's what I'm doing. I'm going to factor a 4 out. So I can factor it. I can factor a 4 out of the 4x squared, right? I can pull a 4 off the x squared. There's not a 4 to factor from the 9, right? But I still can factor it if I write that as 9 over 4. So just think about reversing what I just did. If you multiply 4 back through this parenthesis, you would get back this, right? Isn't that what would happen?
Mm-hmm.
So I just factored a 4 out, And when I pull it out of the 9, it becomes a 9/4. You could do that for any number. If this was 5x squared, right, you could pull a 5 out and this would become 9/5. Any number in front of x, you could pull out of a constant. All right, now what I'm going to do is I'm going to go ahead and use the fact that this is multiplication to take the square root of each of these. So I'm going to basically take the square root of that and the square root of that separately. So this becomes equal to x cubed over, I have the square root of 4, but then I'm going to cube that, and then I have the square root of x squared plus 9/4, but I've still got to cube that, and then dx. So I just split this into 2 separate roots, and now I'm just going to figure out what these are. So the square root of 4 is just 2, right? And 2 cubed is 8. So I'm going to pull a 1/8 out of the integral. And now I have this. Now I can use the formula because now I have x squared plus a squared, right? I have x squared plus a squared.
Mhm.
So when you have x squared plus a squared, what is the trigonometric substitution that we make? X is
Secant theta.
Secant theta.
Tangent theta.
a,
A
A tangent theta.
A secant theta. A secant
a
theta.
tangent theta. Should be tan. Hold on. Should be tan. Yeah. So the whole square root thing will turn into a secant theta, but the substitution we make is a tan theta. So this substitution is the important part here. So we are going to make that substitution that x is equal, what's a?
9/4.
That's a squared.
No, 3/2.
3/2, good. 3/2 tangent theta. We know that the square root of x squared plus 9/4, that will turn into a 3/2 secant theta. And we also know that the derivative of this should be 3/2 times secant squared theta d theta. So you're going to do that for every single trig sub problem. You're going to write down what the trig sub is. You're going to write down what the square root thing turns into. And you're going to write down what dx is. And then you just go back and just paste everything back in. So what
Basically, since there's no integral sign, so we're not doing the antiderivative. We're just doing the derivative of tangent theta.
That's right. We're just, we're just trying to figure out what dx is going to be.
So in this case, it is not legal to pull out the 4 out of the second step you did and call it just 2 over cube just by itself.
Yeah, that's exactly what we did. We pulled the 4 out, right? Hold on. We took the 4 out of here and put it out front, and then we took the square root of it, which is here. Now I didn't show it. That's just 2. And then cubed it, which was 8. And that's the 8 out here.
Oh, I see. So what made it legal was that actually we changed the 9 over 9/4.
That's right.
That's how we, okay.
That 9 has to become a 9/4. You can't just pull the 4 out from the x squared.
I see.
It's got to come from both.
See, now tweaking the problem is the issue.
Yeah. Like I said, I mean, this class delivers, doesn't it? Like it makes a promise at the beginning and it delivers.
Yeah.
It's almost like we're just playing a game here. Like how much shit can you keep track of in your, like how much, right? Like how much can you keep track of? That's what this is all about. How good's your algebra and how many things can you actually process?
Without blinking.
Yeah, without making any mistakes, okay? So, yeah. But you become better, you become better. You come out of the other side of this a better thinker. Okay, here we go. I'm ready to rewrite. So I've got to rewrite x cubed, right? Well, this is x. And so I need to cube 3/2 tangent theta. So I'm actually not going to like cube the 3/2. I'm gonna write 3/2 cubed and then tangent cubed theta. I could have cubed it, okay? I could have put 27/8. I'm just avoiding that for right now. That's the top. The bottom. So the square root of all this stuff, right? All that becomes this, right?
Yeah.
And we have to cube it. Don't forget, we've got a cube on that, right? So we got to cube that. So again, I'm going to have 3/2 cubed, but this time secant cubed theta. That's the bottom. What am I missing?
D theta.
Dx, right? Dx is going to be replaced with this. Don't forget the dx. Students will forget the dx, and if you forget the dx, then you're going to be completely off. Everything's going to be wrong after that.
We can make simplifications here.
Oh yeah, there's a lot of things that are going to happen that are going to be good. Like this 3/2 to the third, 3/2 to the third are gone. This 3/2 I'm just going to pull out of the integral. And let's see, both of those secants go away, and we're left with just one here now, right, on the bottom. Unfortunately, the tangents are still there.
So secant square.
3/16. That's my 3/2 coming out. Tangent cubed theta over secant theta d theta.
I have a question right here. Since it's tangent 3 theta, can I break it down into tangent and tangent square and do the reduction formula? But I'm not sure if the reduction formula works for tangent.
What do you mean reduction formula? I'm not sure what you mean.
The one that we break down with sine square theta, 1/2 sine
Oh,
square.
the half angle. The
Yeah,
half
sorry.
angle.
Yeah,
We don't have a half angle formula for tangent.
oh, okay.
Now, could you split it into tangent times tangent squared? Absolutely. Like you're allowed to do that.
Oh, can we do it like in terms of sine and cosine? So it makes more easier.
That's what I would do, because you got tangents and secants, but they're separated. One's in the numerator, one's the denominator. So I would just get everything to sine and cosine. Like if this is not something obvious, okay, if it's not like a basic U sub, then I would go to sine and cosine. Let's do that. I like that path. Okay, 3/16 integral. Okay, tangent cubed is really sine cubed theta over cosine cubed theta over, now secant is 1/cosine theta, d theta. I can get rid of the denominator if I choose to flip it and multiply. And if I do that, one of the cosines goes away. So I still have a sine cubed on top. And on the bottom, I have, what do I have on the bottom?
Cosine square theta?
Cosine squared theta. D theta. Okay, why don't I give you 5 minutes to see if you can figure out how to go about that.
Now can we use half angle formula?
I'm going to let you figure out, see if you can, in 5 minutes, figure out how to go with this. All right? So it's 1:50. At 1:55, I'm going to come back and see what people have. Enjoy.
Right. Enjoy.
I'm going to put a poll up here. If you figured it out, just vote yes. And if you haven't, you can wait to vote.
I think I have an idea.
Okay. Well, I'm going to still give everyone another minute or so to see. I just want to see out of the class right now, how many of you feel like you got the right thing to do here. Okay, so it's been 5 minutes and looks like 5 of you feel like you got it. Yeah, so someone tell me what they did. Someone who feels like they did okay on it.
Is it possible to split sine cube into 2, leave sine square over cosine square, that equals to 1 plus the integral of sine?
Okay, hold on. You said, can you put sine squared here over cosine squared?
Yes.
And then you put the sine out here to the side?
Yeah, because I think sine square over cosine square, isn't that like 1?
No.
The integral of 1?
That's tangent squared.
Ah, okay.
But actually what you did is right. Who knows what to do with that now?
We can substitute sine squared theta into 1 minus cosine squared theta.
Yep, that's it right there. So here's the thing. If you peel a sine off, you know that can be the derivative of a basic substitution. That would, sine theta d theta would be the derivative of cosine, right? So if you can get everything else in the problem rewritten as cosine, then you're in business. Of course, you'll be off by a negative, but you can take this sine squared and you can rewrite that as 1 minus cosine squared theta using the Pythagorean identity. So now the integral becomes 3/16 integral 1 minus cosine squared theta over cosine squared theta, sine theta, d theta, and now you can make your substitution.
Let u equal cosine theta.
Let u be cosine theta. Yep. The derivative of that is negative sine theta. I'll put the negative on the other side. That's just a basic u sub, right? That right there is that. I replace all my cosines with u, and I rewrite the problem. 3/16 integral 1 minus u squared over u squared, and then negative du. So I'll put the negative on the outside.
Then you can turn the u squared in the denominator into the -2, and then distribute into 1 minus u squared.
Yep. So Minato, you can do it that way. I'm going to just split it into 2. So I'm going to put 1 over this, and then I'm going to put u squared over this.
Okay.
So I'm going to split it into 2 different fractions, which will turn out to be the same thing.
Right.
You'll have 1 over u squared minus u squared over u squared, which will be 1 du. So you have negative 3/16 integral of u to the -2 minus 1 du. And then that's just power rule. So negative 3/16. Okay, now I'm going to do the antiderivative of each one. Antiderivative of u to the -2 is negative u to the -1. And the antiderivative of 1 is u. because we're integrating with respect to u. Which equals positive 3/16 times 1 over u plus u plus c. All I did, sorry, not plus u, plus 3/16 u plus c. All I did there was distributed, and then I rewrote u to the -1 as 1 over u. Still not done. U is what?
Cosine,
Cosine. So what's 1 over cosine?
secant,
Secant. So we have 3/16 secant theta plus 3/16 cosine theta plus c. Still not done?
No. It needs to be written in terms of x.
Written in terms of x, yep. So we've got to go all the way back up to the top to see our trig sub. Where the hell was that? Way up here. Okay, here it is. X was 3/2 tan theta. So I'm going to write that down over here. X was 3/2 tan theta. I'm going to get the tan theta by itself. So I'm going to multiply both sides by 2/3. And now I'm going to draw a triangle. I'll put my triangle above. Be real careful on this. Tangent, right? Tangent theta is opposite over adjacent. So this is 2x and this is 3. And when you do your Pythagorean, this side will be square root of 4x squared plus 9. Any questions? We're almost there. 3/16. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Hypotenuse over adjacent plus 3/16 times cosine, which is adjacent, over hypotenuse. There's a little bit of algebra. These 3's go away. And so my final answer is this. I'm going to put it up here. 1/16 square root of 4x squared plus 9 plus 9/16. Well, I'll put 9 over 16 square root of 4x squared plus 9 plus c.
You can't put this 4x squared plus 9 over the 16 on the left side.
You can't do what?
On the left side of the equation, the answer.
Bring the 9 out.
No, you can you not put the 4x squared plus 9 over 16 instead of 1?
Oh, yeah, you could. Yep. Yeah, you're just saying, could you do that over 16 and then get rid of that? Yeah, absolutely. There we go. That's it.
Now, what was the logic? So you went back when we changed. You said secant was the opposite. Yeah, once you do the change, you said secant was 1 over cosine, and then 1 over cosine was
What I'm
the
using,
reasoning. Yeah.
what I'm using is this, and I know some of you have seen this before.
This.
SOHCAHTOA, right?
Mm-hmm.
You've seen that, SOHCAHTOA? This tells you that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So that's something that maybe you were shown. I'm assuming everyone has seen that. If you haven't, then there it is. It's SOHCAHTOA is the name of a very famous Indian Native American mathematician girl. I'm just kidding, that's made up, but it's a way to remember, Sokotoa, right? So what I was doing was I was saying, okay, if cosine is adjacent over hypotenuse and secant is the reciprocal of cosine, then it should be hypotenuse over adjacent. So it's that flipped, right?
Okay.
Yeah. All right, there it is. So we have our answer. There's the answer. I'm gonna go to Wolfram alpha. And I'm gonna check it. Not that I think we got it wrong, but I'm gonna check my answer real quick. We had integrate, right? We're gonna integrate. It was x cubed over, and then it was 4x squared plus 9. Huh, it's already here. Oh, that's weird. I wonder if that's there because it's in my history, but I don't think I've ever put this problem into Wolfram alpha. Or if Wolfram alpha has just seen this problem before enough, like people have asked. I bet you that's what it is. So look at the answer. This answer does not look like our answer, does it? That does not look like our answer. So that means we could probably do some more algebra if we wanted our answer to look like Wolfram alphas. We could get these and combine these together with a common denominator. So what I would do there is I would put this root 4x squared plus 9 here and root 4x squared plus 9 there, multiply top and bottom. Then I can put them together. So my common denominator would be this. And my new numerator would be these two multiplied, which would give me 4x squared plus 9. And then I still have, what, plus 9 on the other one? Right, which is 4x squared plus 18. Wow, that still looks off.
Then you can take a 2 out.
Oh, take a 2 out, that's all I did. Okay, so take a 2 out of this and reduce it with the 16. Yeah, so it works. All right, 3 problems down. That was a legit problem right there, right? That was a legit problem.
I thought it was fun.
Yeah. Okay, so if you enjoyed that one, I think you're going to enjoy this one too. Next one. Okay, so this one I'm going to pull out of the book. We're going to try and get 5 problems if we can. I'm not going to rush through this one, but didn't I show you all problems from my test last time? I showed
Yeah, you only
right?
showed 2,
That was your
and this
quiz
was something close to it.
Yeah, so I'm going to pull that back up. Wait a minute, where the heck is it? I know I had it open. Give me a moment. I didn't give one like this. That's strange that I didn't give one like this one on the test. Oh, what happened there? Let me see. Yeah, I didn't give one there either. There's a version of that. So look, here's an old test. Look at this first one. This first one is just like the problem we just did, basically, because it's to the 3/2. You see that?
Mhm.
Where did y'all go? I lost all of you. Where are you? There you are. Okay. All right, here we go. Let's do this problem. All right, the first thing you should notice is that we have a square root in the denominator, right? So you should be thinking trig sub. But it doesn't look like any of the forms, does it? It does not look like square root of a squared minus x squared. It does not look like square root of x squared minus a squared. It does not look like square root of x squared plus a squared, right? None of those forms, because we have 3 terms, don't we? Really, the problem is this 6x right here. If that 6x wasn't here, right, then we could kind of do what I did on that previous problem. I could pull a 9 out, and then I'd have something to work with. But we don't, okay? We have the 6x there. So my first step for this one is to do something that I'm sure you're going to love when I bring this up. I'm going to complete the square first. Okay, so this is a college algebra idea. I'm going to complete the square. Now, I'm going to bring up our little poll here. I just want to know whether or not you remember at some point in your life having to complete the square. Yes or no? Not that you remember exactly how to do it right now, but that you have done it.
I've done it.
Okay, so that's pretty much everyone. I think I have one or two people that are saying they have never completed the square. I bet you have, you just don't remember. Maybe you haven't. So completing the square involves taking a quadratic. You only do this with quadratic expressions, and you do something to it. So since so many of you do remember doing it, does anyone remember the procedure for this to complete the square?
No.
No?
Is it negative b plus or minus square root of b squared plus 4ac over a squared?
So what you're giving me is the quadratic formula. You're giving me the solutions to this equation. If it were an equation, if we were setting it equal to 0, what you're giving me is the answers. That's not what we're trying to do here. Completing the square is just a way to rewrite a quadratic to make it look different. So let's, if you don't remember, you're going to have to kind of go on the fly here and see how much of this rings a bell.
Don't we have to
First
let it
step.
equal to 0?
Pardon me?
Don't we have to let it equal to 0 first?
We do not actually. And that was part of the reason why I wanted to ask if you had, because a lot of times when this is taught in college algebra, okay, when this is taught in college algebra, it's taught when we are trying to solve equations. So normally in college algebra, we have it equal to 0. Okay, that's what we normally have. Here, we are not trying to solve an equation. What we're doing is we're working with an expression and we're trying to rewrite it. So let me give you just a quick little background on this. Obviously, I teach college algebra. I haven't taught it in a long time. When I teach completing the square, I teach it the way I'm about to show it to you, all right? But most of the time, students are not shown the way that I'm about to show you. And the reason is because a lot of times, and this is not a knock on other professors at all, but a lot of times in college algebra, your professor does not understand that later on in calculus, you're not going to have the luxury of an equation. And so you can't work with two sides of something, okay? You have to just work within the expression. And so when I show you this method, if it looks a little different, it's because it has to be different. Okay, it has to. So let's just go through it, okay? First step of completing the square is to make sure that the coefficient on x squared is a 1. All right, that's the first step. So I cannot do anything to both sides of anything. So all I'm gonna do is factor out a 9 from everything. 9 comes out. X squared plus 6 over 9 x minus 8 over 9. So this is very similar to what I just did a second ago, right? When we pulled out that 4, same thing. Okay, so now I have this. I'm gonna simplify that because 6 over 9 is 2/3. Okay, so now we've got a coefficient of a 1 on the x squared. That's the first step. Next step is to look at the number in front of the x term, which is which is positive 2/3. And then what you're going to do with that is something special. And the reason we do it is because it'll work out at the end. So does anyone remember what we do with that number? 2/3?
Divided by 2.
Divided by 2. Good. We divide it by 2. So we're going to take 2/3. I'm going to do this on the side, and I'm going to divide it by 2, which is the same as doing 2/3 times a half. Because you would do like a reciprocal again. You'd look at 2 as 2/1, then you would flip it. And that just becomes 1/3. Okay, so this is half. You always take half of the number in front of x. Okay, this is what you always do. First thing, you get the coefficient to be 1, then you take half of the number in front of x. Okay, and I'm going to put a box around that number. Okay, 1/3. That's going to be a special number. It's going to come up later. Now we take that number, we do something with that number, 1/3. You remember what we do with that number?
Add it to both sides.
Close. Okay, so that's the next step after the step I'm looking for. You first have to take that number and square it. Okay, so we're going to take 1/3 and we're going to square it. And 1/3 squared is 1/9. That's our second kind of magic number. So we have two magic numbers. In the completing of the square procedure, we have two special numbers. The first number we get by taking half of the number in front of x. The second number we get is by taking that number we just got and squaring it. Okay, now CJ said we're going to take that number and we're going to add it to both sides of the equation, right? And this is where I'm saying we don't have an equation, right? We do not have an equation. So we can't do anything to both sides.
Do we extract 1/3?
No, we're gonna realize a hidden 0.
Oh.
Okay, so here it comes. 9 x squared plus 2/3 x. And then right here is where we're gonna realize there's a plus nothing and then minus 8/9. Okay, a hidden 0 is a big deal in math, okay? This is actually a very, very advanced idea. And we've used an idea similar to this before. We've taken things like, I don't know, I'm gonna go back to college algebra, like where we had something like this. And we came here and said, oh, we're gonna multiply the top and bottom by something, right? Top and bottom by something, and that right there, this is like a 1. We're multiplying by a 1, and next to everything there's a 1. So we've seen hidden 1s in our life, right? In our mathematical life, we've used hidden 1s a lot. But hidden 0s is a much more advanced idea. And that's what we're about to do. We're about to do a hidden 0 right there. But the way we write that 0 is going to be very clever. What we're going to do is we're going to take our second magic number and we're going to put it there. So I'm going to go 9 x squared plus 2/3 x. And now here comes the magic number. I'm going to add the magic number, the second one, and subtract it. That is 0. Do you all agree that that is 0?
Mm-hmm.
Yep. So 0 is actually those two numbers. But by doing it this way, what we have is that the first 3 terms right here, the first 3 terms are guaranteed to factor. Guaranteed. Every single time it will factor. And what it factors to be is, here I've set a parentheses. Let's put these two together. Let's put those two together right now. I have that -1/9 and minus 8/9. Hey, what's that? -9/9?
-1.
-1. So that's just a -1 out here. Okay. And these first 3, the part in blue, are guaranteed to factor to be a perfect square trinomial. In other words, it will break down to be x, and then it's either going to be a plus or a minus some number here. And guess what that number is?
1
2/3.
9.
1/3.
1/9 we
1/3.
used, right?
1/3.
It's the 1/3 that we had from earlier. And it was positive 1/3, right? So we're going to put plus 1/3 here. So what we're saying is this. If you were to take x plus 1/3 and multiply it times x plus 1/3 and FOIL, you would have the expression that we just replaced. X squared plus 2/3 x plus 1/9. These three terms. And that will happen every single time. So this is our new expression, okay? This is our new thing. Y'all okay with that? We have completed the square. Now I'm going to go back to the original problem. Square root 1 over, I'm sorry, square root, integral of 1 over the square root of, now everything that we have there, the 9x squared plus 6x minus 8 now becomes 9 times, in parentheses, x plus 1/3 squared minus 1 close parentheses. What can I do with that 9? Because it's being multiplied, right?
Put it into two square roots and then
Yep.
take it out of the integral.
Square root 9 is 3, right? And just pull that out of the integral. So that 9 underneath the root becomes a 3 and comes out. And now I'm left with this. All right. I'm going to rewrite it one more time. Okay, here's where we are. Now, if you look at this now and you kind of squint your eyes just a little bit, just kind of squint your eyes and take a look at it. Do you not see that this is really like a u squared minus 1?
Mm-hmm.
Do you see that? So you have like a square root of u squared minus 1, kind of, which is kind of like a square root of u squared minus a squared. But that's a form for a trig sub, right? Like if we had that, we could do a trig sub.
Yes.
Yeah. So that's what we're going to do. We're going to first take this right here, and we're going to make a basic u substitution. U is equal to x plus 1/3. What's du?
du is 1.
1 dx, right? 1 dx, or just dx. And now we're just going to rewrite the integral. Okay, x plus 1/3 is u, so that becomes u squared minus 1. Dx becomes du. All of that work that we've done so far, we're now ready for a trig sub, right? Because this looks like a trig sub. What do we do? See, we're using u instead of x now. But in terms of the formula, we have something that looks like which of these? Option 1, 2, or 3?
I would say 3.
3, because the variable comes first, right? Variable squared minus constant squared. Variable squared minus constant squared. That's what we're looking at. Our variable is not x, though. Our variable is u. So when I do my trig sub at this point, I'm replacing u with what?
With the sign?
Secant
It's a
secant theta
secant theta. A here for us is what?
1.
1. Okay, so this is just going to be secant theta. So u is going to be replaced with secant theta. What can you tell me the square root of u squared minus 1 becomes without having to do any work?
Tangent theta.
Just tangent theta, or 1 tangent theta, but we don't need the 1. And then we also need the du, don't we? The derivative of that, which is secant theta, tangent theta, d theta. That's a derivative of secant. Now I get to rewrite the problem. 1/3 integral 1 over. Okay, all that square root stuff turns into just tangent theta. And the du turns into secant theta, tangent theta, d theta. Are we happy to see that?
Yeah. Because it'll be the integral of secant, right?
Yep, tangents go away, and we just get 1/3 integral secant theta, d theta, which we already know the answer to, formula what, 14? Natural log secant theta plus tangent theta plus c. We've got to get theta back to something, right?
Mhm.
Back to u, back to x.
Back to u, and then we got to get u back to x. So where did we do our trig sub? That's where we did our trig sub, right? So I could draw a triangle based off of that. This is theta. And now notice we're using u, not x here. And I'm going to write that, that's really secant theta equals u. I'm going to write u as u over 1. That way I have a ratio like adjacent, hypotenuse. I have numbers I can put in. So secant's the reciprocal of cosine. So instead of adjacent over hypotenuse, we have a hypotenuse over adjacent. So this should be hypotenuse over adjacent. And that means this side is square root of u squared minus 1. Secant would just be u plus tangent, which would be this part. And last step is to replace x with, replace u with x plus 1/3. But now we're having fun, right?
Mm-hmm.
Very fun.
All right, so I just realized that even with the problems I've shown you today, you're probably still going to get stuck on your quiz. So can somebody tell me in the quiz where the issue came up that I was talking about? Can anyone tell me when you got to the trig integral and you did the antiderivative and you're trying to get from theta back to x, where the issue is?
For me, is where we applied the half angle formula,
Yes.
and then like that's the part where I'm confused.
So when you applied the half angle formula, you got a new expression with cosine 2 theta in it, right?
Yes.
And when you're done, you're trying to get back from theta to x. The problem is that you have an expression in there that has cosine 2 theta, right?
Yes.
And what was your trig sub? Just so I know, what was your trig sub that you used? X was?
X was 5 secant theta.
Okay. So if you go and solve for secant theta and draw a triangle, you should be getting this something like that.
So before that, I'm confused with the part where I have to multiply. Like when I took the antiderivative of the cosine 2 theta, it should be 1/2 sine 2 theta, but
Yeah.
isn't the 2's going to cancel the 2
No.
and the angle? No.
So when you took the antiderivative, we got 1/2 sine 2 theta. When you took
Yeah.
the antiderivative of that,
E-
yeah, these twos don't cancel. The twos, this half and the 2 can't cancel. That 2 is trapped in here. So I'm trying to give you a hint without giving you the answer, all right? When you get this answer and you try and come up with your trig, right? This triangle, the problem with this triangle is this triangle has everything to do with theta, not 2 theta. And inside here you have 2 theta. So you can't
can
just say,
just
oh,
multiply.
sine of 2 theta is just this over this, or sorry, opposite over hypotenuse, and then just double it or something. You can't do that. So my hint to you is to think back to pre-cal. What's another way you could write sine 2 theta?
2 sine theta, cosine theta.
2 sine theta, cosine theta. That's a double angle formula. And the great thing about that formula is that now you have sine theta and cosine theta, which you can get from the triangle. Right? Sine of theta would just be opposite over hypotenuse, and cosine would be adjacent over hypotenuse. So you just take those two answers and multiply them together.
Okay.
Yeah, we don't have enough time to do another problem. Let me see. Maybe we will. Hold on. I just want to see if I can get you something that would help with this. Oh, yeah. How about that? Okay. Let's do this. I've got 9 minutes. Let's see if because this will help you. Let me see if I can do, this is going to be a pretty basic problem, but I think it'll help with the quiz. Let's say we had 4 minus x squared dx. I'm going to move fast, okay, everyone, because of time. So the first thing that we're going to do is make a trig sub. So what trig sub would we use here?
Sine.
X equals a sine
A
theta.
sine theta. So 2 sine theta would be our trig sub. Okay, the square root of x squared minus, 4 minus x squared, that will just turn into 2 cosine theta. And then we take derivative of that, dx would be 2 cosine theta d theta. Okay, so that's our trig sub. Now when I rewrite the integral, all that square root stuff gets replaced with 2 cosine theta. And dx gets replaced with 2 cosine theta d theta. I can't simplify, I can't cancel the cosines. I have to put them together. I'll bring the 2's out. I've got cosine squared theta d theta. Any questions up to that point? I know I'm working fast. Now I'm going to use the half angle identity. This is going to be 4, the half I'm going to bring out of the integral. Then I have 1 plus cosine 2 theta d theta. So that's me just replacing cosine squared theta with 1/2 times, in parentheses, 1 plus cosine 2 theta. And then I brought the 1/2 outside. That's going to be equal to 2. And now I'm going to do the antiderivative of each one of these. So what is the antiderivative of 1?
Theta.
Theta, because the variable here is theta. Okay, plus, now the antiderivative of cosine 2 theta is half of sine 2 theta plus c. That's kind of the place I wanted everyone to get to on the quiz, to that place right there, where you've got the answer, but it's in terms of theta. Now let's get back to x. So I'm going to take this information. I'm going to write sine of theta is x over 2. I'm going to draw a triangle. theta x to this side, when you solve for it, becomes 4 minus x squared. And so here's where things become a little bit weird. First thing we need to know is what's theta, right? Okay, so what's theta? Not what's sine of theta, not what's cosine of theta. What is theta in terms of x? So what we need to do, and we have not done this up to this point, is we need to take that original trig sub that we had and solve it for theta. So to do that, I'm going to take arc sine on both sides, because that's the inverse of sine. So it will kill off the sine on the left-hand side. So I'm coming in with arc sine on both sides of this equation, and that gives me the theta. And theta is then arc sine of x over 2. Y'all see what I did there? Just took arc sine on both sides of that equation. Yeah? So this becomes 2 and then arc sine of x over 2. So that takes care of the theta part. But I still have to figure out the rest of this. And here we're looking for sine of 2 theta. And like I just said, the problem is the triangle is based upon theta, right? Not 2 theta. And you can't just algebraically kill off that 2. So this is where you go to pre-cal. You rewrite this as 1/2 times 2 sine theta cosine theta. And if you're wondering where that formula is, although everyone in here should probably get that formula programmed in pretty quickly, because it's one of the big ones. Here we go. Where is it? Right here. Double angle formulas. Sine of 2 theta equals 2 sine theta cosine theta. That's the formula I'm using right there. When I teach pre-cal, I make sure that my students have that burned in, because I know they're going to need it here. All right, now these 2's will cancel now. So I'm going to have plus, that's my plus. Now, what's sine of theta? I just go to my triangle. Sine is opposite over hypotenuse times what's cosine theta? That's adjacent over hypotenuse plus c. That's it. You could do a little simplification there. You can distribute the 2 through and stuff, but that right there, that's the answer in terms of x. Are there any questions on how I did it? No, I went a lot faster through that than I thought I was going to go. No? All right. So your weekend is pretty much over. You know, if you got to do your trig sub homework, then your weekend's pretty much filled up now. This is one of the most important sections for homework that we have the entire semester. Specifically numbers 39 through 59. Okay, these are hard problems. These are long problems. These should take you a while. There's a lot of stuff involved, right? But if you can get through them and you can make sense out of them and you feel comfortable with them, you're ready then. Like you're ready for at least this portion of the test. So don't try and avoid this section. And remember, I've got my homework solution videos. For this particular section 6.2, I'm guessing that it's a lot. Yeah, I think we already talked about this. Just under 4 hours of homework solution videos for this section. Yeah,
but that's like 12 hours if we want to review it.
Yeah, so like, you know, that's me doing the homework, knowing which path to take, right? So if it took me 4 hours to do this homework, it should take you at least 3 times that, right? If you're really truly trying to figure it out on your own. So it's a huge task. If you look at the next assignment, 6.3, right? That homework assignment's almost 3 hours. So I told you in the beginning that the 2 hardest sections for integration are 6.2 and 6.3. Those are the 2 hardest sections. So have at it, you know, have at it. The schedule, where are we on things? We're supposed to have a test on October 13th, which would be still a little over 2 weeks away. Today we were supposed to do what? See, we were supposed to start partial fractions today. So I think we're like a day behind right now. We're about a day behind. So what I'm going to do is probably trim out, like I said, I don't know if I said this to you all. My plan is to keep the test the same day, but 6.6 is 2 different days, right? There's the first half and second half. We'll just do the first half and then have the test. And then the second half will be on the next test.
Okay.
Okay. So persistence, right? Suffering. I told my other class about suffering. Did I tell you about suffering?
No.
Okay. So, oh, it's 2:40. If you've got to go, you can go. And have a good weekend and do your homework. There's a saying, I used to do a lot of cycling, try to do some triathlons when I was younger. And I did, hundreds, thousands of miles on my bike, right? And there was a saying that when you were training for an event that, like let's say in the triathlon you had to do a 50-mile bike ride, you probably needed to do like 2,000 miles on your bike before you do that 50-mile bike ride. So while you're sitting there trying to do your training and you're on your bike and you're sitting there doing a 3-hour ride and you're suffering, right? You're sitting there suffering. There's a saying of what you're doing is you're putting deposits into the suffering bank. Okay, so there's the bank of suffering. And every time you're out there training suffering, you're putting a little bit of money, a little bit of currency into that suffering bank. And then when it came time for the competition and you're sitting there and you're trying to push, and you're trying to reach that next level, that's when you can make the withdrawal. That's when you can go to the bank and take a little bit out. You can start withdrawing that money that you put in. In other words, it's a terrible analogy, but it's the more pain that you have during this homework part of this, trust me, you'll be able to draw on that during the test. That is going to be where it'll pay off. On that test where you're sitting there looking at a problem and you're like, I've been here. I've suffered through this before. Like I'm okay, Does that make sense?
Yeah.
Okay. So enjoy the suffering. Enjoy it. It's part of the ride.
And this is just the beginning too.
Yeah, well, you know what though? Like, look, I'll be honest with you. If you can get through this, if you can get through these 2 sections, I think you're really not going to face a challenge again like it until we get to probably 8.2, 8.3, 8.4. Like the other stuff we're going to do in here, I think everyone's going to be we're going to be able to exhale, okay? Like as soon as we get past 6.4, or 6.3, I should say, when we get past 6.3, then 6.4 is, even though it's on the schedule, it's not even a section. It's just 6.4 is titled Integration with Tables and Computers. So all I tell you for 6.4 is, hey, there's Wolfram Alpha, right, that can do these things, and that's all I say. Like we don't do any problems. So really, after 6.3, it's going to be an opportunity for us to be like, okay, let's just take a breath. Let's get through the next few sections. They're not as bad, and then we get to chapter 8, and that's where things start to look very different and weird again. So you're almost there. Come on, you can do it.
So now that I'm looking at the exam, are we going to be tested on integration by parts, even though we were somewhat tested on exam 1?
Well, if you go back and look at the integration by parts problem I put on the last test,
Yeah, it was super easy.
Those were very basic ones.
Mm-hmm.
It's quite possible that you may not even see an integration by parts problem on the next test. To me, an integration by parts problem right now is down here, like in terms of difficulty.
Yeah.
Like
If you know this tricks of then integration of parts,
it's everything is starting to become very relative in this class, right? So when we walk in, we're like, okay, power rule, U substitution, right? U substitution, we're like, wait, I'm supposed to see something in its derivative, and your mind's like, what? Now it's like, please give me U substitution, please. You know, that's what I want. I want that now. This other stuff is, so everything is so much higher level now that the integration by parts, I'm not sure testing on that. You probably would like to have a problem like that on the test, right? I mean, because it might actually be an easier problem for you to do. Yeah, I don't know. I'm just talking.
Yeah.
Yeah, and I showed my other class the test, so I'm going to show, not the test, but I showed them my entire last test that I gave last semester. Please do not sit here and start taking pictures of the screen and think that this is your test. But this just gives you an idea of what an exam 2 looked like a year ago for one of my Cal 2 classes. So this first problem is a trig sub, that's 6.2. The next one, that's the quiz problem I gave you. The next one is a 6.3 problem. That's a partial fraction problem. This is a partial fraction problem. This is an integration by parts. But now we have limits of integration. We have numbers that have to be accounted for. This is another problem, improper integral. This is another improper integral, but this integral requires partial fractions. So you can see from this test, there was really only one problem here. That's trig sub, right?
Mm-hmm.
I mean, that just happens to be the way that test looked. Now, let me see, here's another test. Trig sub, partial fractions, partial fractions, partial fractions, partial fractions. Integration by parts. Yeah, so the reason why I can't put a lot of trig subs on the test is because they take forever.
It takes,
right?
yeah.
They take so long. You know, if it takes me 30 minutes to do one problem in class, you know, I can anticipate it's probably going to take you 45 minutes at least, right? So
If we know what we're doing.
yeah, so. All right.
All right.
Yep. Have a good weekend.
Thank you.
Thanks, Professor.
Y'all have a good one.
Wait. I have a question.
Yep.
So I don't want you to give me the answer. I just want to make sure I'm on the